Right, okay. Welcome everyone. So, I'm just going to give it a few more minutes for people to jump onto the live, if people are indeed joining us for the live. We're going to do a quick recap, if you like, of the slow geological cycle that we covered last week, and we're then going to see how the slow geological connects to the fast biological cycle, and from there we're going to see what that fast biological cycle actually looks like, because what you'll notice is that this operates over shorter timescales than the slow geological cycle, and it involves a far greater range of processes. So what we'll do, we'll get started and we'll kick off with it, because there is quite a lot more to cover than in the slow geological cycle. So fast biological, that's where we're going for. That's what we're going for tonight. So just if you are joining on the live, if you could just let me know like where you are joining from, it's good so I know where my audience are coming from, I guess. And if there's anything that you would like me to go through tonight, maybe you've studied the carbon cycle, and maybe the fast biological cycle is something that you'd like to go over. Again, certain elements, certain components, it's completely up to you, or you can just kind of absorb the content while I go through it. But if there's anything that's not clear, please just do put something in the comments. I am streaming through another platform tonight, so it's called StreamYard, so there might be some delay in terms of when you write a comment and then when it comes up onto the comments box. So do bear with me on that. I'm experimenting with different tech, but I think the live this week, from the looks of it, looks a hell of a lot better than the one last week. I think the lighting's a lot better, and I think you can see me and the board and the writing more clearly. So hopefully that will be something that you will find a positive thing. Right, so slow geological cycle was what we were looking at last week, and your main processes here were occurring over timescales of around 100 to 200 million years, hence the slow geological cycle. And if you remember, one of the core components of this that made it slow was that we are reliant on the movement of carbon, through the lithosphere. And that movement of carbon through the lithosphere is primarily a consequence of tectonic plate movement. And we know that tectonic plate movement takes place at millimeters per year, and it relies then, the natural release of carbon dioxide into the atmosphere is from volcanic outgassing, which takes place at a rate of around 0.15 gigatons per year. So it's really slow. And what you'll see is that the fast biological cycle, not only does it take place over faster timescales, there's often greater volumes of movement between the stores in the fast biological cycle. And that's kind of what makes it so fast. That turnover of carbon is a lot more rapid. So our link point, I guess, is, and how we move between the slow geological and the fast biological cycle is, as we already stated last week, it's because carbon has made its way into the atmosphere, and now it's in the form of CO2. So what we established last week, if it wanted to stay in the slow geological cycle, what would happen then is it would go down the route of acid rain, and then it would go down the route of chemical weathering, and then it would make its way into the oceans, and then it would sink to the ocean floor and become part of the lithosphere once more. Now, what we're trying to do this week is talk about how it can go into the fast biological cycle. So there's a way that it can jump from the slow geological cycle into the fast biological cycle. It fancies a bit more fast turnover. Now, the way that this is achieved primarily is via a process that we all know, because we should have done this at GCSE in your sciences, is via photosynthesis. So we take photosynthesis because it's CO2 plus H2O plus sunlight. And what this does is it locks carbon into what's called biomass. Okay, so it locks carbon into biomass. And this biomass can exist on both the terrestrial biosphere, which is where we are as humans. And the primary way that that will take place is through vegetation, but it can also be sequestered into biomass in the oceans. And the way that it's achieved in the oceans is by the little green things in the top of the oceans or in the surface layer of the oceans, which are phytoplankton. So if it wants to enter the fast biological cycle, it can do it one of these ways. So it'd be either photosynthesis via vegetation into the terrestrial biosphere. This takes place at a rate of around 110 to 123 gigatons of carbon per year. So you can see that's significantly larger, isn't it, than the rates of volcanic outgassing. So photosynthesis is one of those processes that is its large volumes. Phytoplankton, they are responsible for 50% of global photosynthesis. So they contribute massively to this movement from the slow geological cycle to the fast biological cycle. So it's essentially thinking about how carbon is moving through living things. Yeah, so the turnover time, this is a really important concept in the fast biological cycle and the slow one, to be honest, but your turnover and your residence times are a lot smaller. So what we're going to do tonight is go through primarily the oceans. So once it's in the oceans, what does the fast biological cycle look like when it's in the ocean store? But I think it was worthwhile going through how do we go from slow geological to fast biological. And then remember, we can go back into the slow geological cycle because once we get into the oceans, it can just get caught up in this cycle again. So I'll clear the board and we'll go through the oceans because there's a lot to go through, because there's these things which I'm sure you all remember called the pumps, and it's the pumps that will give you that understanding of how carbon moves around the oceans in the various ways. So I need the whole board for this because there's a lot of pumps to go through. So this is how I do it with my students at school anyway. So they have big whiteboards in front of them and I get them to just continually draw the pumps, every lesson, try and drill the pumps with them. So we got to that point, didn't we, where we know that there are phytoplankton that exist in the surface oceans. Now, what we describe this layer as here is something known as the photic zone. So the photic zone is the area within the surface oceans that can be exposed to, or there is sufficient sunlight for photosynthesis to take place. So there we go. We've got the sunshine, shortwave UV radiation. So what else do we need? Well, we need some carbon dioxide. Now, carbon dioxide diffuses directly into the surface oceans. Yeah, so that's the flux there. It's known as diffusion. And the direct influx of carbon dioxide takes place at around 92 gigatons of carbon per year. Now, that 92 gigatons of carbon per year is the influx, but just as there can be the direct diffusion of CO2 into the oceans, it can also be released. And we'll come back to this idea, but this is known as direct gaseous exchange. But that takes place at around a rate of 90 gigatons per year. So you can see that the diffusion of carbon dioxide into the oceans, there's a net influx of carbon into the oceans. So they are a net carbon sink. That's really important to remember about the oceans. But what that does is it puts dissolved CO2 into the oceans. So that can be utilized by phytoplankton as well. So they've got the sunlight, they've got the CO2. There will definitely be some nutrients involved, things like iron, etc. And then what can happen is carbon dioxide is fixed into biomass. Now, this is known as the biological pump. Yeah, so this is known as the biological pump. Now, your biological pump is essentially the food chain. So once it's in the phytoplankton, and that will usually be stored in the form of carbohydrates, just as it would be in vegetation, it then moves through into your zooplankton, which then are eaten by small fish, which are then eaten by larger fish, which are then eaten by even larger fish. And so there's almost that biomagnification of carbon. But as you move, or you increasingly move through the food chain, it's increasingly stored as fats and proteins and DNA. So the biomass, or the storage of biomass, as you move through the food chain, it becomes larger and larger. So that's the first stage. Now, the beauty with this is is that these are living things. The carbon that's contained within these is like more mobile, if you will. So this doesn't remain here. Yeah, the carbon doesn't remain in this store. It's mobile. It can be transported. So this fish or this whale or this shark can swim to the surface and then can deposit nutrients here. So can this. It can swim to the surface. It can swim back down. So this is a very mobile layer, this layer here. The other thing we've got to think about as well is that your first layer that takes place, where photosynthesis takes place, sorry, this is known as these are your net primary producers. These are your net primary producers. So the primary productivity that takes place here. Now, the role played here is not just carbon dioxide in. The role here is also oxygen out. Yeah, so it's carbon dioxide in, oxygen out. As it moves through the food chain, we know that there is also a mechanism by which carbon dioxide is also sent back out. And the name of this flux, obviously, is respiration. So as carbon moves through larger organisms, there will be increasing carbon that is returned to the atmosphere via respiration. Oh, brilliant. I've got someone in the comments. Hello, thank you for joining. Right. So that's the food chain. So you've got to be certain of what your inputs of carbon are and what your outputs of carbon are. You can't just talk about the fact that carbon is moving in. A lot of the questions that you'll get in the exam are around regulation of the carbon cycle, how these things maintain balance within the carbon cycle. So you can't just talk about in, or you won't get as many marks as you could get. You've got to talk about this regulation, and look, it's carbon going in, carbon going out, carbon going in, carbon going out, carbon going in, carbon going out, and it's part of this equilibrium. Yeah, so that would be the biological pump. Okay, sometimes it's called the organic pump as well. Now let's go over to here. So the pump we're going to go through here is the carbonate pump. Right. So why this is called the carbonate pump is because the carbon here is stored in inorganic form, yeah, usually in the form of calcium carbonate. Yeah, so usually in the form of calcium carbonate. And calcium carbonate within marine organisms is usually in shells or exoskeletons. So we bring in some of the content from the slow geological cycle. So if you remember, chemical weathering carries dissolved carbonates via solution into the ocean store. So what we've got here are carbonates. Now, some of these carbonates precipitate, so they solidify straight away, and then they will go down to the ocean floor. Sedimentation will take place. This is the carbon that is currently locked up in the slow geological cycle. Now, there's a minimal amount of carbon where this will happen. It's around 0.1% of the carbon that makes its way into the oceans, down wells, and becomes part of the lithosphere again. So it's a minimal amount. The remainder remains in the ocean store. So again, it's just talking about the sheer volumes that are involved here, or the sheer lack of volumes that are involved in that slow geological cycle, are the very reason why it's called the slow geological cycle. What happens to a lot of the carbonates is that they become part of the shells of crustaceans, mollusks, or given their collective name, marine calcifiers. Yeah, so they'll become part of marine calcifiers. What also classes as this is this here, which is coral. So as part of the inorganic pump, coral, crustaceans, mollusks, anything with a tough calcium carbonate exoskeleton is part of that carbonate pump. And once again, there can be that movement between both elements here, because something from over here could consume something from over here. Obviously, the shell will be left. But from both sides, there is the possibility in both cases for death to occur. That's a dead crab, by the way. And then I'll try and do my best effort for a dead fish. There you go. And they can both fall down to the surface ocean. Not the surface ocean, sorry. The sea floor, and become part of the lithosphere. But like I've said before, minimal amounts of this will make their way down to the ocean floor. Okay, so that's your carbonate pump. So the predominant movement here is kind of cyclical, if you like. This one is a bit more downwelling going on. The final one, and I think this is probably one of the most important pumps, particularly considering its importance at the global scale, is the physical pump, which is also known as the thermohaline circulation. So what I am going to have to do here is trim back a little bit, so I've just got the room. I'll trim back on this one because we do involve a little bit of this. So I'll trim the carbonate one just because we kind of know about the carbonate anyway. Now, your thermohaline circulations, this is the final pump, which is the physical pump. And for some reason, students struggle with this just a little bit. Some students, I'm not saying all of them. So the thermo part and the haline part are the ones that are the bits of this phrase that you need to focus on. Thermo implies heat or temperature. Yeah, thermometer. You've got that. Haline is something to do with salt. And if you remember, those of you who've studied coasts, when we talk about a halocere, that is plant succession that's taking place in a salt marsh. So it's kind of, we know that heat is involved and we know that salt is involved. That's its circulation driven by differences in heat and in the temperature of the water, and the salinity of the water. So we looked at two areas of the planet, the poles and the tropics. Yeah, so we've got the poles and the tropics. Now, the temperature difference here is the most obvious point to start with. So obviously the water up here is cold. Yeah, so we've got cold water here. The water here is warmer. In the poles, it's increasingly saline. Yeah, whereas in the tropics, it's less saline. Now, both of these factors here will lead to differences in the density of the water. When something is colder and saltier, it increases the density. And what that leads to is this process here known as downwelling. Okay, that's essential. If we didn't have these temperature differences, we wouldn't have a thermohaline circulation. It would be very unlikely that we had a thermohaline circulation. So the very fact that we do relies heavily on the fact that we've got significant temperature differences in the water in the tropics and the water at the poles. Or more to the point, the water in the poles needs to be cooler than the water everywhere else. So then we get that downwelling process. Now, the importance of this is because, remember, when something is cooler, you get an increase in the diffusion of CO2 into that water, and it remains in that water. Yeah. So this is a very important point in terms of regulating the concentration of carbon dioxide in the atmosphere. Again, if we don't have the temperature that we do in the Okay, my apologies. There seems to be some technical glitches going on here. Right, we're back on. Sorry, technical glitches. I'm not sure why. Not sure why at all. Right, so that downwelling process takes place, and it takes it into the deep ocean store. So the importance of taking that carbon down to the deep ocean store is that there is increased residence time. And this is where the majority of carbon is located. So you have around 38,000 gigatons of carbon in the deep ocean store, whereas there's only 1,000 gigatons of carbon in the surface ocean. Then what happens is, obviously, it's transported all over the place. There's these thermohaline currents, and then we get upwelling in areas of the tropics. So we get upwelling at certain points. So a classic example of an upwelling current that brings nutrients to the surface is the Humboldt current off the coast of Peru. Now, this is really important because not only are we bringing CO2 up to the surface, we're also bringing nutrients. Yeah, we have to bring nutrients to the surface because the nutrients support the biological pump. So we're supporting the base of the food web. That's really important. For the CO2, and again, this all comes back to the regulation of the carbon cycle. It provides a way when in warmer water, CO2 is less soluble, so then it is released into the atmosphere. So once again, we're maintaining that balance within the system. Yeah. So that's the oceans. Fast biological cycle in the oceans. You've got to know your three pumps. You've got the biological over here where it's moving through the food chain. You've got the carbonate, which is part of the slow geological cycle. So you know about that. And you've got the thermohaline circulation, which is because we've got temperature and salinity differences between the tropics and the poles. That means we get the downwelling of water in the poles. And that's the thing that kickstarts that whole ocean circulation system, which obviously, as we know now, supports not only atmospheric concentrations of carbon in the atmosphere, but also supports your biological pump. So they all support each other. So that's your fast biological cycle. There's a really good question, and I can't remember the year of the paper. I think it's 2018, 2019 maybe, and it's all about it's 2022. That's how sad I am. It talks about how the oceans regulate the composition of the atmosphere. And what's really important for you to note is that it's not just about CO2. It's not even just about O2 as well. It can also be about, it's a source of water for the atmosphere. There's a lot of water that is evaporated from the oceans that ends up in the atmosphere. So they are a really important store, a really significant store in the fast biological cycle. But just look at all the things that are going on. So that's the oceans. So what we're going to move on to now is we're going to come out of the oceans and come on to the terrestrial biosphere. But while I'm clearing the board, anyone got any questions at all on the oceans, the importance of the oceans, anything I've just been through, anything that you need me to go through again, just pop something in the meeting chat. I'm more than happy to go through anything again. So when I see something pop up, then we'll go through it. Now, let's go to, we're on land, okay? No waves, we're just on land. So when we're talking about the terrestrial biosphere, oceans is relatively simple in comparison. We've got two things that we can talk about. We've got vegetation, and we've got soils. And we know that the major flux that takes place is photosynthesis. Here we go, photosynthesis, CO2. Now, CO2 then ends up in biomass, just as it did in the oceans. So a lot remains the same in terms of how we explain that process. Now, something that I teach my students is something that you will have done at GCSE when you did ecosystems. When we move from biomass, it can then go into this stuff here, which is litter. Now, this is particularly something that if you're watching in the UK, which I imagine the vast majority of you are, or all one of you that's watching is, this litter can then make its way to the ground, and that's what's happening right now. Winter in the UK, it will produce a lot of leaf litter. And then there's another process that we can talk about that takes place, which is decomposition. And it's that process of decomposition that you'll see that taking place with fungi and detritivores, bacteria, microbes. It's that process of decomposition that then takes carbon into the soil store, because in the soil store, we've got this organic layer known as humus. Yeah, so this organic soil layer known as humus. So photosynthesis can take place, CO2, we know this before, we said it's around 123 gigatons of carbon per year. We know that in the evening as well, vegetation can respire, so there is the release of CO2. We know that vegetation isn't just kind of trees and flowers and that kind of thing. Sometimes vegetation can be things that consumers can eat. So once again, just like in the oceans, you have to explore, excuse the very bad cat drawing, but then we can go to our consumers and it goes through the food chain, and we know that they respire. So these are the main processes we want to think about in the terrestrial biosphere. The deeper the carbon goes in the soils, the more increased the residence time and the reduced turnover of carbon that takes place. And then it's very important that you see this as a cyclical relationship, because the fertility of the soil then determines how much the biomass or how much the vegetation can then grow. So it's that cyclical relationship within ecosystems. So the concept of photosynthesis, when we think about the terrestrial biosphere, is inextricably linked with another concept which is known as NPP, and this is net primary productivity. Net primary productivity, turnover of carbon. So turnover of carbon is just like this. Yeah. So sorry, this is a message that's come through on the chat. The carbon turnover is how quickly it goes into a store and then is lost from a store. So it's literally just that. It's another way of saying reduced residence time. Yeah. It's one of those. In geography, the best recommendation I've got for you is write in such a way that makes you seem like you're very articulate You'll pick up words. It's like a high level, right? Because it's an essay writing subject, you're going to skew that examiner's subconscious bias towards a higher level mark when you're using good key terms. So, yeah, carbon turnover. If you don't use it, it's not a deal breaker, but it's just another thing that you can add in that impresses the examiner. So the photosynthesis is linked to net primary productivity, and that is the ability of an ecosystem to fix carbon into biomass. So we know that some ecosystems are better at fixing carbon than others. Yeah, we know that for a fact. So if we draw a globe down here, and again, this is what I do with a lot of my students, and let's draw the different latitudes. It's the easiest way to think about it is to think about it in terms of latitudes. And the main latitudes that I get my students to think about are the following ones. And we can look then at variations in rates of photosynthesis, variations in rates of decomposition as well, and then you've got the ability then to not only evaluate the importance of photosynthesis and decomposition in different local scales, but you can also comfortably answer a question that might ask you about why there are differences in the rates of photosynthesis and decomposition, because you don't know what you're going to get. So latitudes we'll look at 0 degrees latitude, we'll look at 30 degrees latitude, we'll look at the mid-lats, which is where we are in the UK, and we'll look at the poles as well, and then we'll look at some more specific ecosystems as well that we can think about rates of these different things varying. So if we look at photosynthesis first, and I'll put number 1 here, and we think about what conditions are needed for photosynthesis to take place. Ideally, optimal conditions would be where there is increased insolation, where there's increased insolation. Fancy word for high concentrations of solar radiation per meter squared. So your average highest rates of insolation obviously are here at the equator. The other thing that you need is you need water, or you need rainfall. So where there's the highest rates of insolation, highest rates of rainfall, we also obviously need nutrients as well. So we need insulation, we need sunlight, water, and nutrients. Carbon dioxide is a given because it's in the global commons. So it's not necessarily something that is not in abundance. It is. We definitely have carbon dioxide. So what we're thinking about is the greatest rates of photosynthesis will take place where these are highest, and therefore net primary productivity will be highest where we've got the highest degrees of photosynthesis. So in that respect, we think, right, why would there be differences in the rates of photosynthesis? Let's first look at differences in insolation. Well, the strongest differences, or the most apparent differences in insolation, are between 0 degrees latitude and the poles. So we have variations here because there's low insolation here, high insolation here, therefore net primary productivity is higher here. Once again, we can zoom in on water. So water, again, the equator, if you do the water cycle, and this is where we get a lot of crossover with the water cycle on the terrestrial biosphere, this is the ITCZ, which is the intertropical convergence zone, which is where we will get high volumes of convectional rainfall because we get a lot of evapotranspiration. So at 0 degrees latitude, very high rates of net primary productivity because high insolation, high rates of rainfall, and there's also a relatively high nutrient content because, well, we'll come on to that, but because there's such an amount of biomass that makes its way back into the soils. Now, it doesn't have the highest nutrient content, and we'll come on to why when we look at decomposition. Where do we compare this to? We would compare it to 30 degrees latitude, which, if you remember, is the edge of the Hadley cell. Now, at the edge of the Hadley cell, remember, if we have rising air here, because of evapotranspiration, we then have descending air here, because remember, these are our air cells, and this is your Hadley cell. The golden rule of rainfall is that air must rise. Where we have descending air, that's where we have high pressure. So there's not a lot of cloud cover. There's lots of clouds here. Air is dry and it's descending. So we have very low rainfall here. This is where you'll see a lot of your deserts. So your Sahara Desert is along here. A lot of areas in the Middle East and North Africa are along here. So there's like Egypt, Syria, Saudi Arabia, those kinds of countries. So we have very low net primary productivity. So we have massive variations. Mid-latitudes, the variations are less spatial here and they're more temporal because it depends on the seasons. So we'll have seasonal differences in net primary productivity. And that, if you remember, is to do with the axial tilt of the Earth, which means insolation is in higher concentrations in summer. Yeah, so we have summer rays. We're through that now. We're well out of that in the UK. And that's when we'll have high rates of net primary productivity, and then there will be low rates of net primary productivity when the concentration of solar radiation moves south. Yeah, so the southern hemisphere now will be going through there, will be coming into their summertime as we go into our winter. Well, they'll be in their summertime. So that's photosynthesis and the importance of photosynthesis in fixing carbon. So this is why, remember that along this is where you've got a lot of your tropical rainforests. And tropical rainforests, you'll see various statistics put forward, but this is where around 30% of global photosynthesis takes place. Yeah, or maybe I think it's 30% of photosynthesis in the terrestrial biosphere takes place, or 30% of net primary productivity. Tropical rainforests do have the highest levels of photosynthesis on the planet, particularly in the terrestrial biosphere. You can be certain of that. Right, the second thing that we talk about is decomposition. So what's needed for decomposition? Now, with decomposition, slightly different conditions. Rather than say sun, we need warmth, okay? So for decomposition to take place, it's not the case that you need sunlight. You just need warmth, yeah? You don't necessarily say water, but you do say moisture. And we'll come back to that because there's a slight little but with moisture. And you also you need warmth, moisture, and you need oxygen as well. So it differs slightly from photosynthesis, but it's really important that you know these conditions. Now, there's a few rules with decomposition, and this is where it starts to get a little bit complicated and where students start to get a little bit confused in terms of the importance of these processes in certain places. So the highest rates of decomposition will take place along the ITCZ because it's warm, because it's moist, and there's plenty of oxygen because this is where we have the tropical rainforests. Someone's just asked if I can explain El Nino. Absolutely. More than happy to explain El Nino. Once I've been through differing rates of decomposition and organic and inorganic soil content, I will absolutely go through El Nino. I love explaining El Nino. It's one of my favorites. Okay, so high rates of decomposition. Now, high rates of decomposition doesn't necessarily mean highest carbon content in the soil, okay? When decomposition takes place, the faster the rate of decomposition, the more carbon is lost to the atmosphere, and I'll explain that. because it's the fungi and the detritivores that are decomposing the organic matter. And because they are living things, they respire. And that is CO2 being emitted into the atmosphere. So if we want the highest concentrations of carbon, or the highest amount of carbon, to be locked up in soils, what we would want is a situation where there's large volumes of dead organic matter added to an ecosystem, and the rates of decomposition are really slow. Okay, we have such a thing. We have such an area on the planet, and this area is something that you will have studied in the water cycle, but you won't have linked it to carbon storage. And this is a wetland. So what happens is organic matter will make its way down to the bottom of the swamp or the bog or whatever you want to call it. And then there's something that we're missing. Decomposition will absolutely take place. Yeah. But it will take place very slowly, because at the bottom of the wetland, we are suddenly now in anaerobic conditions, yeah, which means there's a lack of oxygen. So dead organic matter will be added to this ecosystem at a faster rate than decomposition can take place. So what builds up over time is this very carbon-rich soil known as peat. Now, given a few 100 million years more, and this will then turn into a coal deposit, but often, you know, humans get in the way. We've realised that this is a particularly fertile patch of soil, so maybe we'll use this for agriculture, or it contains a lot of carbon, so maybe we'll use it as an energy source. So that's just what we do. We just get in the way of things, really, don't we? So there's areas on the planet, places like Scotland. I'm not going to attempt to draw Scotland. I'll have a go. There you go, Scotland. It's not to scale, but it's my best. Where there's peatlands and where carbon is stored for many years. So peat bogs, swamps, marshes, they are incredible carbon sinks. But again, it's just a way of, again, carbon moving through in different ways and staying in places for different amounts of time. Now, with anaerobic decomposition, you will produce a lot more methane. So it's not that there isn't any carbon released, but it's just released in a different gaseous form. Okay, so that is the essentials of the fast biological cycle. The other thing you probably need to know as well is obviously differences in rates of decomposition as well, as determined by warmth. Yeah. So the poles and, high latitudes, there's a lot of soil that is permafrost. And once again, because this is, again, it's carbon-rich soils. They're very, very carbon-rich because they've not undergone that process of decomposition, because it's kind of frozen in time. So the fungi and detritivore activity is low because there isn't the sufficient warmth. Yeah. So once you know the rules of photosynthesis and decomposition, it becomes almost like a game, trying to work out, well, where do we have high rates? Where do we have low rates? Where will we have high organic carbon soil content? Where will we have low organic carbon soil content? You can tell here, can't you, that we'd have low organic soil carbon content. Yeah? So that's it for the fast biological cycle. So I hope you found that useful. Obviously, it went on a little bit longer than the slow geological cycle. So it's at this point that we can go into the question and answer, and I can answer literally any of your A-level geography concerns or questions, or if it's on NEA or anything like that. And I will be going through El Nino first, and then anything that anyone wants me to go through, I can. Or we can just sort of leave it there for tonight. But I've got, a few more views tonight than I had last week. What I'm hoping is that I'll keep getting more and more views, and that people will start to get more and more from these sessions, and we'll get a bit more interaction, because I need to kind of know what people are struggling with to know what to use. So I do carbon cycle because it's the one that most people kind of struggle with the most, and it's for upper six. This is what they'll be studying right now a lot of the time. So I'm going to get rid of this, and if you do want to see a more polished version of what I've done here, I always do like a follow-up edited video that you can, and it'll be a kind of shorter video than the one I've done here, so it'll be more edited, and there'll be music on it and stuff. So right, onto El Nino then. So the basics of El Nino. You know that El Nino has to take place in the tropical South Pacific. So once you've got once you've got it located, then you know where it takes place. So Australia and Indonesia is on this side, and Peru is on this side here. So there's another question comes through that. So the slow biocarbon cycle is only underground. So that's not a thing. The slow biological carbon cycle, I'll come back to that. Yeah. So Australia, Indonesia. Now, what you have to know about here is that there are these things called trade winds. So what I'm going to go through first is a normal year. Yeah, so I'll go through a normal year first. During a normal year, the trade winds will move, westward. Yeah, so there's westward trade winds. And what these trade winds do is they create currents. Yeah. Now these currents will transport warm surface waters, because we're in the tropical South Pacific here, so the surface oceans are being warmed at all times. So they will transport warm surface waters this way, off the coast of Australia and Indonesia. Now, when you have an area here, an area of warmth, you've got to imagine it's almost like a hob, yeah? So it will heat the air above it. So the air above it here, there's kind of like a 4 to 5 degree temperature difference between here and over here. It's much warmer. Now, when you have a heat source, what happens to the air, the overlying air, is it becomes less dense, and then the air rises like this. And when you have rising air, what that will make is convectional rainfall. So during a normal year, there will be more of this taking place. Yeah, there'll be more of this taking place. So you'll have an expected amount of rainfall. And then, because of the way that air cells work, you will have air that returns towards Peru. Now, this is known as the Walker loop. So you have dry air that is descending and creates high pressure in Peru, so they have less rainfall. Now, the crucial terminology here is that this is a normal year. Yeah, it's a normal year. So if we were to then say that now Peru is in drought, that would be incorrect. Yeah, because the definition of a drought is rainfall that is below the multi-year average. So they just have expected volumes of rainfall, and they just have expected volumes of rainfall. Right, that's a normal year. So we start the cycle there, because this is known as ENSO cycles. So if we have a normal year here, from a normal year, then we move to an El Nino year. Hang on, no we don't. So we go from La Nina to El Nino to normal year. Yeah, good. We're currently in this. So we're currently in an El Nino year. We should, next year, go into a normal year. Fingers crossed, yeah? Now, what happens in an El Nino year? After a normal year, after a La Nina, is this. the trade winds either weaken or reverse. So let's say they reverse. The warm surface waters here are now blown over here. Oh, okay. So the whole system is reversed. The whole system is reversed. So now we get the increased convectional rainfall over here in Peru. So Peru, because they're not used to this volume of water, experience floods. So during an El Nino year, there'll have been times this year where Peru experienced floods. Yeah. And then we have the dry descending air returning over here. So now Australia and Indonesia are experiencing high pressure and less rainfall than they are used to. So that is now something we can categorize as a drought. Now, when it's rainfall in the initial stages, we would class that as a meteorological drought. Yeah, and then as there's reduced infiltration, as there's reduced percolation, as reservoirs start to dry out, what that will then probably escalate to, particularly as we start to go into our reservoir stocks and withdraw from aquifers, will then probably escalate to a hydrological drought. And if it goes on any longer, maybe there'll be a famine drought. Who knows? Not likely in Australia. So that's an El Nino year. And then your La Nina year is just like an exaggerated version of a normal year. So that's when Australia, having been used to large volumes of rainfall, now has even more rainfall, and there's floods over there, and then there's like really extreme drought over here. So the last La Nina year, so we have an El Nino year now. Prior to this, there was a triple dip La Nina. So the thing you need to know with El Nino is that climate change is meaning that these El Nino and these La Nina years are sticking around for longer. Yeah, so you know the season of drought, you know, for how long the country remains in drought because of an El Nino year is extending. So that can really prolong socioeconomic hardship that's a consequence of El Nino. Now, the other things that you can then bring in are, it's not just Peru and Australia and Indonesia that suffer as a consequence of El Nino. What we have, when this happens, there's changes in air pressure, and a change in air pressure here will create almost like a domino effect, where there's then going to be a change in air pressure in other areas of the world as well. So it will have a knock-on effect on other areas with their air pressure. Now, these are known as teleconnections. Yeah, and some classic examples of teleconnections are how an El Nino year affects storms in the US. It's how it affects your seasonal rainfalls in some African countries as well. So one of your classic teleconnections examples is how in an El Nino year, it can then often lead to drought and famine in places like Ethiopia. And it's because of the knock-on effects of air pressure. Now, what you don't have to know is why the whole system of El Nino takes place in the first place. We don't know, you know, we're not 100% certain. There's theories, and I don't even know what they are, but you as A-level geographers don't have to know that. You just have to know that this takes place, and there's a cyclical nature to it, and the ENSO cycles last for anything between 3 to 7 years, and that's extending because of climate change, and there can be teleconnections where it can have knock-on effects in other areas of the world. So it's not just isolated to the tropical South Pacific. The effects spread globally. The effects spread globally. All right, so that is El Nino. Has that, I don't know if you're still watching, has that answered your El Nino question? If it has, just give me either a thumbs up or something else that says, yes, I'm happy with that explanation. And what I can do now is come on to the slow biocarbon cycle being underground. Yeah, let's just unpack that a little bit. Right, so your slow biological... Right, I'll come back to that question. Your slow biological cycle, this won't take long. So your slow biological cycle is not a thing. You will either have slow geological, the majority of which takes place, yes, in the lithosphere. The majority of carbon is held in the lithosphere. Or you have your fast biological. Now, within the fast biological, and this is where I think you might be coming from, is that there's varying degrees of what we mean by fast, because it can vary from minutes to like thousands of years. Yeah, whereas your slow geological is like hundreds of millions of years. So there's faster and slower processes in the fast biological cycle. Slower things, do take place in soils. Fast things are in like the surface oceans and vegetation. Yeah, so that's where I think the confusion might be there. But they're the two cycles that you want to talk about. So coming back to this, so we're learning a theory as a pattern which may or may not vary. I don't fully understand the question. It's a pattern which may or may not vary. You just have to learn El Nino as this basically happens, and it happens on it's a cyclical it's a cycle, and it does take place, but it remains in place for varying amounts of time. Yeah, so I guess there is that kind of, it may or may not vary. So the things that are certain are that it will happen. Like there will be ensocycles. We will go back to a normal year. We will then go to a La Nina year. We will then go to an El Nino year. So these are the certainties. What is also certain is teleconnections. There will also be knock-on effects on other weather systems around the world. Yeah. Oh, I see. So I would learn it as a process rather than a theory. Yeah, so it's kind of like it's a bit like some AO1 that's just like, here's a case study. So learn it as it's almost like a bit of a crossover between process and case study. So it's a specific process that happens in a very specific place in the world to very specific places, and there's very specific outcomes in those places. Learn it as that. Yeah, I get your point now. Yeah, so learn it as that. Yeah, so almost treat it like a case study. It's just a very specific process in a very specific part of the world that does take place. So you won't get an El Nino happening. It doesn't happen anywhere else. Yeah, it's not like wave refraction, which can take place at all coastlines. Yeah, it's not like don't know. But processes, I know exactly what you mean. Yeah, it's not like hydraulic action. Right, so could they ask about knock-on effects in a test, like giving the Ethiopia example and ask a reason for it? They probably wouldn't ask specifically about that. That's more something that you could bring in to show a greater range of knowledge about El Nino. So what they tend to do at A-level is they'll base a question on something like drought. So it might be sort of, assess the extent to which physical factors contribute to drought to a greater degree than human factors, or assess the relative importance of physical factors compared to human factors when you talk about drought. So your physical paragraph could either be that you just explain El Nino and then you get as far as Australia and Indonesia and you stop there, or you could then go on to talk about teleconnections and then bring in Ethiopia. Yeah. If you stopped here, you're probably giving level 2 levels of detail, which is still good. If you went here, you're giving level 3 range of knowledge, which is going to get you higher marks. Absolutely. But I don't think they would ask you anything specific about, explain teleconnections. Yeah, you can always bring it in. There is a question actually where I think it's a 3-mark question in one of the previous water cycle examples. I think it's either the 2020 or the 2021 paper, and you have to, you can see where it becomes drier during an El Nino year, and then there's all these other places on the map which are like there's wetter here, drier here, wetter here, drier here. You probably could talk about it in that, but you don't have to. I don't think you would get anything as specific as talking about teleconnections. I think they just want you to know the basics of. You've just got to know about El Nino. Okay. Right. Any other questions? And I'll be as quick as I can. But this is great. This is exactly what I wanted from this live, is people asking questions, and I can sort of give you almost like free tuition, if you like free one-to-one tuition. This is what I wanted. But if we've not got any more questions coming through, okay. Oh, amazing! So you're in a different country, right? Okay, yeah. I mean, yeah, brilliant. Thank you for the feedback. So what country? So it's 1 p.m. for you. Yeah, it's 7:30 at night for us. So whereabouts are you joining from? Because I've officially gone global. Yeah, good. No, you're welcome. You're absolutely welcome. So yeah, just let me know. I'm not proposing we go any longer. One is, oh, brilliant, you're in India. That's amazing. So there's a few of you watching, and you're in. That's amazing. You're in India. All right. Well, thank you very much. And hello from the UK. Brilliant. I can tell all my students that I've officially gone global. Right. Okay. We'll call it a night there because it's an hour. I'm about to do bedtime with my daughter, so I need to go. But yeah, I'll be doing a similar thing next week. So not the fast biological cycle. What I propose that we do next week is look at this idea of an unbalanced carbon cycle. So once you know about the cycles, what you can then do is say, if through various human activities we change anything, either by changing land use or by releasing CO2 into the atmosphere, what are the knock-on effects on all the cycles? Yeah, so we'll have a look at that next week. But thank you very much. Thank you for joining, and I will hopefully see you as many as possible next week. Thank you very much.